So, welcome to the first review lesson as we tackle measurement. The very first slide that I have for you is actually doesn't really even apply to the unit. It's more just to get your brain back in the thinking about chemistry mode. So, if you take a look here, first off, do me a favor, write down 25 degrees Celsius somewhere up here. Just add the phrase 25 degrees Celsius. This whole situation takes place at 25 degrees Celsius. So just don't do it right now. I'd rather you listen to me. But yeah, remember my guidance for pictures. If it is an image that looks chemical, draw it. If it's an image that looks stupid, like the little baby on the next slide, you don't have to draw the kid. All right, so brain juice is flowing. Here's what I wanted you to think about. This is called a density column. It's 4 different things that were mixed together, and they've separated. So what you're supposed to think about is what would make them separate based on items you learned last year. Okay, well, here's what I know. It gives me the state of matter of the 4 items, and it lets me know that one is water and one is mercury, and then I've got comparative densities of all the substances. Anybody remember a density fact last year? If you mix 2 things with different densities together in the liquid form, which one goes to the top? The one with less or more density? Less. Very good. All right. And if you're like, I didn't know that, you're fine. All right. It's fine. You don't have to know everything right off the bat from last year. But yeah, less dense floats was a phrase that I use. So then the question is, what is that? Well, water is below it, and water is 1. So if this is above water, it should have a density that is generally less than 1. How many options are there? Yeah, hexane and ethyl alcohol. These are the only 2 items that it could possibly be. So how do we differentiate between them? Well, one's nonpolar and another's polar. Now, we are not going to cover polarity during Unit 1. All right, again, this is just an opening think about it. But I used the phrase last year, like dissolves like. What that meant was if you have 2 substances that have the same polarity, they will like to mix together. And they won't separate nicely like this column does. So if water is polar and this is staying separate, then which of these substances is it most likely? Yeah, the answer is hexane. You can write hexane in that blank. Because since hexane is nonpolar, it is way less likely to mix with the polar water. What do you think the other blank is? Anybody just want to shout it out? It is bromine. And here's how they know it's bromine. They know that this item has to have a density greater than water but less than mercury. All right? So it can't be gold, right? Gold would be way down here because it's got the highest density. But it could be bromine or aluminum or dichloromethane. Now, it's not going to be the dichloromethane because it's got the same polarity as the water again, so the water and that item would mix together, but they're staying separate. How do I know it's not aluminum, though? That's a good answer. It doesn't tell us the polarity of aluminum, but you know how you wrote 25 degrees Celsius a moment ago? Anybody know what the common description of 25 degrees Celsius is? Room temperature. Yeah. 25 degrees Celsius is about the temperature of this room. And at room temperature, aluminum is solid. You want to know how I know that? Are y'all okay being on the video if I turn it towards that? You can say no. I don't want to pressure you. But anyway, in case you didn't know, these are my friends. But the other thing you might not know is that the colors of the letters up here actually tell you the state of matter at room temperature. And aluminum, since it's a black symbol, is solid. They all are. The blues are liquids, and the greens are gases at 25 degrees Celsius. Cool, right? I get to be the star again now. Now, again, I just wanted your brain to be thinking, oh, yeah, I learned stuff last year. None of this really applies to what we're doing today. But are there any questions as we truly get started? If you're watching this at home, you should have already written down your slides. I will flash the slides quickly to the screen, and if you need to see them through that, like you're a student from another school or something, pause the video when I do that so you can copy it down before I teach. Okay. Sorry, I have lots of fans from other schools, I'm told. So we have to make everybody happy. Mm-hmm. Significant figures. Yeah, huge part of the class. It's embedded in every unit that we do because there's numbers in all of our units. So we've got to be good at this. If you don't remember what significant figures are, it's simply the idea that our measuring devices can't measure out all the decimals your calculator can. And the stuff that we measure in the lab, those are the numbers that we need. Like, for example, you have a calculator. If you do 22 divided by 7, you don't have to, but you can if you want to. Right now, if you go 22 divided by 7, you'll get a ridiculously long number that we don't have any devices that could measure that many decimal places. So what we do as scientists is if I do a lab, I base the number of digits I report using sig fig rules so that if someone wants to repeat my work, they know exactly how precise I was instead of me coming up with wild numbers that a calculator was assuming instead of a real life situation. In order for that to work, though, we have to be globally on the same page on how significant figures work. So let's remember the rules. By the way, note taking skills. If I write it on the whiteboard, you definitely write it in your spiral. But as I'm talking and you're having eureka moments when I'm just up here doing my thing, I hope you fill up the margins of your notes and stuff. That's good college note taking. Don't think you only need to write when Cummings says, you better write this down. All right? Take responsibility for your education now. If I say something that seems like it made something else make sense to you, jot something down. Be in good habits. Significant figures are made up of 4 rules. We apply these rules to expressions to count digit for digit. That's 33 grams. I want to know how many sig figs there are. So we're going to go through the rules. Rule number 1 states that non-zeros are significant. In this case, we're dealing with two non-zero numbers, therefore 2 significant figures. The non-zero numbers are the easy ones. It's the zeros that cause us issues. But they're both significant because they're both not zero. Look at this next expression. $303 milligrams. Rule number 1 is non-zeros. Rule number 2 is sandwiched zeros. If you have a zero that is stuck in the middle of a number, it's not starting or ending the value, then it is significant. Sandwiched zeros are significant. Therefore, there's 3 sig figs there. Rule number 3 refers to zeros that end a number. If you have zeros at the end of a number, whether it be one or a bunch of them, they come as a package. They're either all significant or they're all not. And if you read rule number 3, it says ending zeros are significant if you can see a decimal drawn by the author of the expression. For example, if we have 300 kilograms, there's no sandwiched zeros, but we do have a leading zero. I'm sorry, we do have a non-zero, so automatically significant. What's true about those other two zeros? They are not significant because zeros that end in number are not significant if you can't see a decimal, and there's no decimal shown. So there's only one sig fig there. But what if instead of writing 300 kilograms, what if I had written 300 kilograms? Now we have three sig figs. Non-zero. But since there's a visible decimal anywhere in the number, it doesn't matter where it is. If there's a visible decimal anywhere, the package at the end becomes significant. Finally, rule number 4. Leading zeros, zeros at the beginning, are never significant. Please notice how rule number 4 has no designation of decimals. Y'all mess this up for some reason because the decimal throws you off. But if I have 0.033 liters, how many sig figs do you see? There's 2. Non-zero, non-zero, and both of these are at the beginning of the number. Decimals have no effect on this rule. So there's only 2 sig. Right, we're about to draw our first card, our first real card of the school year. I'm going to give you a number to analyze. Let's see how you do. I want you to look at the green expression and tell me how many sig figs you think there are. Not out loud. You're just thinking. All right. Oh, by the way, we're about to do this card draw thing. Y'all, no one cares if you get it wrong. All your classmates care about is the fact that I didn't pick them. All right, they right or wrong, they're not judging you. They're just so happy it's you that's having to speak. So, no pressure. Relax. Life is good. Let's go over to cluster 5. Seat 2. Aspen, I found you. Hey, Aspen, how many sig figs do you see in the green expression? Yeah, because it's you've got the Aspen bird. So the guess is 6. Do y'all agree or disagree? You're right. Just so good. You're right. You can pass the bird. Yeah, 6 is the right answer. Look. Non-zero, non-zero, non-zero. Sandwich, sandwiched. Ending zero sometimes. See the decimal? So it is. Leading zeros never are. Questions? Oh, avoid dead babies. Do y'all remember what the dead baby rule is? I mean, avoiding dead babies, it's a good life lesson also. But in here, avoiding dead babies, it means this. If you're going to write 0.5, you should never write 0.5 like that. What should you do instead? 0.5. The reason this is no dead babies is because way back when there weren't computers and doctors and nurses just handed each other's reports to give doses of things, like if it was zero point 0.5 cc's of a drug that needed to be given to a child, what there was lots of instances of happening was the doctor would write it like this, zero point 0.5 cc's, and hand it off to the nurse, and the nurse would administer 5 cc's because they didn't see the decimal. And if you give 5 cc's instead of zero point 0.5 cc's to a baby of any medicine that matters, the baby dies. If the doctor would have written it like this, it would have drawn way more attention to that decimal, and the baby wouldn't have died. So, write your small numbers with leading zeros because they're insignificant and they don't change those rules. One of the College Board's favorite applications of sig figs is your ability to read lab equipment with it. There's an FRQ type question like this every single year. This past year, it was a graduated cylinder question. So you've got to know how to read these. Here's the rule. When using lab equipment, you will always estimate 1 digit more than the device can actually measure. For sig fig purposes, you are responsible for always measuring 1 extra digit. Here's what I mean. Look at this top ruler. As I examine that top ruler, I see these little hash marks for the graduations. That's what the device is counting. And if you examine it, they're actually counting the tenths place. This is 1.1, 0.2, 0.3, 0.4, 0.5, and so on up to 1.9 and finally 2.0. And it does the same over here. So what that means is that the device itself is counting these two positions, the ones place and the tenths place. So your job then, if you're going to report what it's measuring, is going to be to estimate 1 more digit. In this case, to the hundredths place, which is why you can see that it goes 2.55 in that spot there. It's going out to the hundredths place. But if you look at the bottom ruler, you'll see it's far less precise because there are no little graduations. The bottom ruler just has the ones place. So all it's doing, it's only measuring that spot because it's so much less precise. So what's your job in lab? You will estimate 1 more digit. In this case, the tenths place, which is why it goes out to 2.5. Right? Because the line that they're measuring is in between the 2 and the 3, but they can't go to the hundredths place because the measuring device is less precise. All right, no questions. Let's see if you really get it then. I want you to read the other two devices. We're going to draw cards. Using those rules, read the other two devices. Now, for graduated cylinders, you read at the meniscus. I'll give you that word in a slide many units from now. But that means that when it does its little dip, you're going to record from the lowest part of the dip. So for this one here, read it from the lowest part of the water's dip. You're welcome to chat with someone near you. I love collaboration. Let's draw some cards. Remember, no one cares if you get it wrong. Let's start with the graduated cylinder. You're just going to tell me what your reading is. Let's head over to cluster 4. And we will talk to C. Hey, 4-1, what did you get for the graduated cylinder? The guess is 39. Do y'all agree or disagree? I disagree with 39. Anybody having second guess, you can shout it. No. 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 38.0. This is the only correct answer. Why is it the only correct answer? Well, this graduated cylinder is counting to the ones place. I mean, look, that's 30, 32, 34, 36, 38, 40. It's counting all of the ones places, which means these two are for sure. You must estimate one more digit, though. And it's hitting 38 on the nose, right? It's swooping right on the hash. 38.0. Let's draw another card. Let's go over to cluster 2. Seat 5. What'd you get? 2.25. 1.26. The guess is 1.26. Do y'all like or dislike that answer? I think it's pretty good. I think she did everything she was supposed to do. I put 1.25 when I wrote it down because it looks like it's in between the 2 and the 3. But whatever. She followed all the rules. That measuring tool is going out to the tenths place, right? 0.5, 0.6, 0.7, 0.8, 0.9. It's going to the tenths place. So she estimated to the hundredths place. And she knows it was between 1.2 and 1.3. I thought it was right in the middle. She thought it might have been a little closer to the 1.3, which is totally fine. Questions? Now, the other most common application of sig figs in here is going to be just arithmetic. But in order for us to multiply and divide on our calculators correctly, we have to be able to round. This is a third grade skill that I'm just going to very quickly review. I do want to give you this heads up, though. If during this lecture or the other 5 on that roadmap, if there's a moment where you're like, why is he going so fast? Like, slow down, Cummings. 2 things about that. First off, starting next unit, I will slow down. This is assumed review because you've already sat through it all. So I don't want to go too slow because I'm assuming that you passed honors chemistry. But the other thing is I have honors videos of me doing everything slower. So if during any of that roadmap, if you're like, oh, you did stoichiometry too fast, sir, I get it. I've got multiple honors videos of me teaching stoichiometry at a snail's pace that I can send to you. You just got to ask me for it. And then you can sharpen up on these remedial skills. Just communicate with me. Write this down. (1,567 kiloliters). How many sig figs are there? There's 4, right? None. There's no zeros, so that should be really easy. Yeah, 4 sig figs. But what if I needed there to be less? What if I needed you to write the same number, but instead I wanted you to make it be 2 sig figs? You would have to round it. So here's what we do. We always keep the digits, the significant digits, furthest to the left as the most important. So I want there to be two sig figs. So I'm going to keep those two digits. The significant figures furthest to the left, which means the other numbers are going to go bye-bye. The 7's going to go super bye-bye, and the 6 is going to go a little bye-bye. And what I mean by that is the digit you're eliminating that is right next to a digit you're keeping has the power to bump that digit up. As you know from your elementary days, if this number is 5 or higher, it's going to bump up its neighbor. If it's less than 5, it'll do nothing. So what will the 6 do here? It's going to bump the 5 up to its next digit, which in this case is a 6. So now those are the two digits that I'm keeping. Is that what it rounds to? No, because if I owed you $1,567, you would not be okay with me giving you $16 instead. That makes no sense. So what do we add for placeholders? Do you see how these two numbers are similar to each other? See how it makes sense? Right? 1567 rounds to 1600. As long as you don't put a decimal anywhere, those zeros are insignificant. Therefore, we're now at two sig figs. Let's do another one. How many sig figs do you see right now? 3 is the right answer. There's a sandwiched 0. The leading zeros are never significant. What if I wanted there, though, to instead only be 2 sig figs? I want to change it to 2 sig figs. Well, we're going to keep the 2 sig figs furthest to the left, which are none of those. We're going to keep those two. Now, we can keep the other zeros. We're just ignoring them. But those are the two that definitely need to stay as my 2 sig figs, which means he's going bye-bye. Does that 4 have any power over that 0? No, because it's got to be a 5 or higher based on elementary knowledge. I've now rounded it to 2 sig figs. Well, they're insignificant and you want the number to be the same, right? If I just wrote 40, then the numbers are nowhere near each other. Now they're pretty much the exact same number because leading zeros don't count. Okay, so let's read the new slide then. How do we apply this to our arithmetic? Well, we need to remember first off that multiplying and dividing have rules, but adding and subtracting have different rules. So let's do the multiplying dividing first. Let's go 81.05 times 0.010. Use your calculator and get an answer. Did you get the brown number? But that's not the answer. If you were to report that brown number, it would be completely wrong. Because here's what your slide says. If you're multiplying or dividing, your answer can only have a number of sig figs equal to your least precise starting number. Here's one of my starting numbers. How many sig figs are next to my finger? There's 4. Here's my other starting number. How many sig figs are next to my finger now? 2. My answer must equal the smaller of those 2. Therefore, 2 sig figs. So what I'm going to do then is I'm going to keep those 2 digits because I'm trying to get down to only 2. So the 5 is going to just automatically leave. The 0 is going to have the ability to maybe play a role, but it won't because it's not big enough. The green number there is the only reportable number to get a correct answer. Dividing works the same way. Adding and subtracting is different, and y'all mess this up because you like to mix up the worlds. So let's look at what adding / subtracting follows. Write this down. 4.45 plus 233.1. Get an answer on your calculator. As the slide states, adding and subtracting, the sig figs don't even look to the left of the decimal. The whole numbers are ignored, which means we don't care about the 4, we don't care about the 233, and we don't care about the 237. I mean, we care. It's like use the numbers, report the numbers, but you don't ever have to doctor those for sig figs if you're adding or subtracting. The only thing you focus on is the items to the right of the decimal. The amount of digits to the right in your answer has to equal the least precise of the starting. So, do you see how right here there's 2 digits and right here there's 1 digit? That means in my answer, the digits to the right must be what? 1. And right now it's 2, which is no good, right? The smaller number is winning. So I don't care about the 237. Leave those alone when you're adding, subtracting. But this 5 has to go. So what's the final answer? And that is the only acceptable answer to that addition problem. I mean, I'm just going off digits to the right of the decimal for adding, subtracting. So this number had 2 digits to the right, and this decimal had 1 digit to the right, and 1 is smaller than 2. No questions. I'm killing it. Of course, Canvas is going to give you lots of practice in all these skills. Finally, we're going to end with unit conversions. There's a slide after this slide that I'm not going to get to. Don't sweat it. That's my problem. I will get us there. But let's convert some units. As you know, you can't have naked numbers in here, meaning anytime you report a number to me, there should be units after it. All right, grams, liters, whatever. Moles, we like moles. There's prefixes that can be put in front of any of those units to give them different meanings when we're dealing with things that are really big or really small. All right, so instead of just being moles, we could have micromoles. Instead of being liters, we could have kiloliters. And the ability to have units convert into different versions of themselves is a cornerstone of science. So we have to make sure that we're good at it. The way that I teach this is this blank in the middle is the base. That would be where there's no prefix at all, the moles, the grams, the liters. But then you can put these words in front of them and go up and down the ladder to convert. When I say ladder, what I mean is that the prefixes that are up here are larger items than the ones that are down here. So if you're climbing upward, then the units are getting bigger. And if you're moving downward, the units are getting smaller. And that's important because of this rule here. If you're doing a conversion and your unit's getting smaller, that means your number has to get bigger. And vice versa, meaning if your unit gets larger during the conversion, the number gets smaller. And we slide decimals to do this. Let me show you what I mean. Let's say that I gave you this number, 0.066. What are those units? Somebody say them. Gigagrams. Yeah. It's not a good Friday until someone's made you say gigagrams. If I had that many gigagrams, I want to know how many megagrams is that? Can we convert gigagrams to megagrams? Well, here's what you would do to think it through. You would find gigagrams on my little chart up here. And you would say, well, if I'm starting at giga and I'm moving to mega, are the units getting bigger or smaller? Smaller, because you're moving down the ladder, right? If the units get smaller, your resulting number should get bigger, right? It's always the opposite, inverse. So we're going to slide the decimal in that 0.066 to get a bigger number. Make sure you slide it the right direction. But how many times do you slide it? Well, that's what these exponents are. Like if I was moving from kilo to hecto, it would be a 3 to a 2, which would be one slide, because I know how far 3 is from 2. That's not what we're doing. We're moving from giga to mega, which is 9 to 6. And how many spots are there on the number line to get from 9 to 6? 3, right? 9, and then 8, and then 7, and then 6. It's 3 slides. So let's slide the decimal 3 times while making the number bigger. There's the number. I'm going to slide the decimal 3 times to the right. 1, 2, 3. Because by doing that, instead of it being 0.066, the number becomes 66, which is a larger number, like we wanted it to be. And we've done the conversion. Let's do another. This next one's going to come with a card draw in the middle, so focus. $750 microliters. If I have 750 microliters, I want to know how many hectoliters is that? Is the unit getting smaller or larger? Larger. Do you see how micro is near the bottom and you have to move up to get to hecto? The unit's getting bigger, so the number needs to get smaller. So I know that my resulting, whatever I write, better be smaller than 750. Now look at the exponents associated with micro and moving to hecto. And here's where my card draw is going to come. Don't answer out loud. How many slides? Looking at the exponents of micro to hecto, how many times do you have to slide the decimal to get from a -6 to a +2 on a number line? Let's head on over to cluster 2. Steet. Hey, 2-4, what do you think? The guess is 4. Agree or disagree? I disagree also. We're starting at -6, right? So let's just count together to get up to +2, right? So it's 4 to -2. That would have been the good answer if it was -2. But it's a +2. So -6, -5, -4, -3, -2, -1, 0, +1, +2. How many clicks did my hands just go? 8. Count again. For those of y'all that are saying 7, count it again. All right. But yeah, I need to slide this invisible decimal 8 times while making the number smaller, which we had already decided. So it's 1, 2, 3, 4, 5, 6, 7, 8. Of course, those blanks that I created will be zeros. And it looks like there are 5 of them.
Is it kind of like a train track?
Yeah, but when we do those, I mean, that's more dimensional analysis. That's for, I mean, you can train track this.
Yeah, it's a lot easier.
Yeah, I think this is. I mean, when you're doing stoichiometry, you have to use the grids because there's too much going on to just figure it out like this. But now, hey, a couple nuances here. All right, let's be extra smart. How many sig figs are there above my finger right now in green? There's only 2 because there was no decimal, so the 0 is insignificant. Do you see how my Oh wait, what is it? 45? Oh God, stupid Cummings. Okay, there was 2 sig figs, and I ended with 2 sig figs. Ta-da! Y'all have a great day. Yeah, let the sig figs need to stay consistent. Those of y'all still watching the video at home, I just want to also add that this number later that this number is annoyingly long, and scientific notation would be a shorter way to write it. Again, there's a video from last year on this, but the rules of scientific notation state that you have to start with a number between 1 and 10. So to make this number become between 1 and 10, the decimal would have to be between the 7 and the 5. It would be 7.5. So that would be 7.5. Then it would go, you can come say hi if you want. Then it would go, have a good weekend. You would put times 10, which I like to use a capital E, which means times 10. Okay. And then how many times do you have to slide the decimal to make it be in that spot for 1 to be between 1 and 10, which would be 1, 2, 3, 4, 5, 6. So it would be e to the -6 because it's a number smaller than 1. And this is an easier representation of that long, annoying black number. But if you want more scientific notation practice, I can link you to that.